Stanford seminar. Today we have a very interesting topic in helioseismology titled Recipe for Imaging Global and Local Solar Internal Magnetism by our speaker Srijan Bharati. Srijan completed his undergrad at the Indian Institute of Science, Education and Research, Kolkata, during which he also worked at the Department of Science and Technology in India, the National Center for Radio Astrophysics in India, and the Max Planck Institute for Solar System Research in Germany. He's currently a fifth-year PhD candidate at Princeton University, in which he received a Centennial Fellowship, and during which he also recently worked at the COFFIES Summer Program in Astrophysics 2021 on Ensemble Astroseismology hosted by MPS. So please join me in welcoming Srijan. And then without further ado, Srijan, please go ahead.
Hello, thank you, Matthias. Hi, I'm Srijan. I'm, as I said, a final year in my PhD right now. And the talk that I'm going to present today would essentially be two of my personal favorite topics during my thesis, which involves global and local scale magnetism in the sun. And for the global case, it can also be extended to other stars, as I'll show. So this is called the recipe because with good reason, because we haven't yet done an actual inversion. We just have the methodology very recently, and we are underway to do the inversions with real data right now. And the three images in the very first slide are just demonstrative of the broad topics that I'll be covering. The first one is the global magnetic fields in the sun, and this is from dynamo simulation. The second image is from one of Matthias Rempel's simulations, where one side of the image is observations and the other side is simulation. And this is something that really fascinated me when I saw this image for the first time. And I was asked by Sami Solanke to guess which side is simulation and which is observation. I mean, luckily I got it right, but the fact that it is so close, and yet we cannot do a formal inversion of what the subsurface of a sunspot looks like is sort of both fascinating as well as it sounds a little frustrating to me in some sense. And the last image is just a funny demonstration of a specialized kind of basis functions that I'll be using in this new methodology called Slippian functions, where you can basically define your own domain in physical and spectral space. In this case, it's like a cat and a duck, respectively. And as I'll show it really makes a big difference in how well the inverse problem is constrained. All right. So going forward, so why do we care, right? Like, why do we care about the interior of the sun or the other stars? And the simplest explanation is whatever is happening in the plasma environment of a planet, be it in the solar system or other exoplanets, is ultimately rooted in what's happening inside the sun or other stars. And this is one of the results of simulations from my master's thesis, where we show how the planetary magnetosphere protects the atmospheric losses of the planet itself, driven by the stellar winds. And people in COFFIES who work on space weather, this is possibly the only slide for you. And thereafter, I dive deep into the interiors. Okay, so the outline of the presentation is as follows. First, I'll be introducing normal modes of the sun. This is the broad methodology that I follow in my studies. And I mean, as possibly a lot of you know already, the interior of the sun is sampled by these acoustic modes, which you can actually observe. And there are these deep gravity modes, which is very challenging to observe as of now, which exists very close to the core. And as of now, we will be only talking about the P modes because that's what's observable. And the second idea that I'll be introducing is basically sensitivity kernels, because only when you know how the physics of the system behaves as a response to what's existing inside the star or the sun, can you actually carry out formal inversions. This has been successful for rotation, sound speeds, and density, but till now, well-defined closed-form expressions for general configuration magnetic fields was not really out there. So such inversions were out of question. But with what we have done and shown, I think that's a promising avenue. The next thing is the Lorentz stress kernels that we have derived. Fortunately, none of these equations are something that I'll be going deep into. It's just to show how they look like, which is quite cumbersome. I'll demonstrate through a toy problem how such sensitivity kernels actually show up in the A coefficient measurements of the sun or also possibly other stars. This is one of the new topics that I'll talk about. And the second thing that is also new would be Cartesian mode coupling with, again, the magnetic kernels in the local Cartesian system instead of the global. And finally, I'll show that the traditional method of doing such inversions poses a poorly constrained inverse problem. And when you change the basis to Slipian functions, which again are hand-defined or hand-drawn contours of your feature of interest, these inverse problems are much better constrained. And I'll show some examples of what we are getting very, very recently, as recent as I think last night. So yeah, let's get into the introductions. So this is just Fourier transform. If we have a wave in time domain, which is in this case a superposition of two sine waves, you can split that up into its own frequency components. And if you project it back into frequency space, that's nothing but two peaks. And this essentially forms a big part of everything that I do on a day-to-day basis. And in 1D, these are just strings which oscillate, like when you plug the string in a guitar, they oscillate in various modes of oscillations, and one of them might have no nodes, another might have a single node, and so on and so forth. But when we are trying to do the same thing for a 2D surface, which is a sphere for the sun or other stars, we need an analog, which in our case would be spherical harmonics. And it's exactly the same as a string. The very first spherical harmonic is just an analog of a flat string. So if you just think about wrapping that string around the surface, it's just a constant value all across. The second one is where you have a single nodal crossing, which is the analog of the very first sine curve along the sphere. So you can either have a zero crossing along the equator or along one of the great circles or longitudes. And yeah, we can go on with this. So the beautiful part of this is that the reason why we use this is because it's a basis function, and you can decompose any random pattern if you can sum up to infinite number of spherical harmonics. And it's important to treat the problem in the correct basis in order to optimally constrain all our inverse problems. And in this case, as I'll show, we will deal with a specialized kind of spherical harmonics called generalized spherical harmonics, which is useful for tensor fields. So in this picture, I show something which is a scalar field, which could be something like a temperature or anything that you can imagine that's a scalar. But for our case, it would be the magnetic field second rank tensor, which is the Lorentz stress, which is BB. And I'll show all of this in a few slides. But just as a simple demonstration, here it's a very nice simulation or demonstration where you can sum up all these spherical harmonics to make the cosmic microwave background. So the point is, you can decompose any surface or any pattern on the surface. And just to give a more intuitive picture, this is how each of the modes of oscillations in an exaggerated fashion would pulsate. And when you look at the sun, you can observe it in the Doppler field and decompose it into such eigenstates, with each of which would look like one of these spherical harmonics, and they would pulsate with their own characteristic eigenfrequency and spatial pattern, which is the eigenfunction. And when you combine all of them with appropriate weights, you get the observed sun. And this is just a concise representation of everything that I told you, where in the x-axis is the angular degree of the particular spherical harmonic, and in the y-axis is its characteristic eigenfrequency, or the frequency with which each of these spherical harmonics pulsate. And the power contained in these pulsations is given by the color map. And you see these clear ridges, and as I guess all of you know, these are the radial orders of oscillations, meaning each of these ridges belong to a particular number of nodal counts as a function of radius or depth. So if we are talking about the very first branch, which is the F mode, it doesn't have a zero crossing as a function of radius. And as we go higher and higher in these branches, they start having 1, 2, and more radial crossings. So that's just a way to make a three-dimensional basis, where, as I already showed, the spherical harmonics form the basis in 2D, which will be given by quantum numbers such as L and M, as in the hydrogen atom problem. And in depth, it's given by these radial orders, which is labeled as N. So the pipeline in global helioseismology is summarized in the slide, where the leftmost panel shows a Dopplergram, or a cartoonist version of the Dopplergram, where the red dots are pixels that's red shifted, and the blue dots are pixels that's blue shifted, depending on whether it's coming towards you or away from you. And from this, you can decompose the sphere in its own spherical harmonic components, and each spherical harmonic is now going to oscillate at a certain in a certain way over time, and you can extract a time series out of that. And yeah, so it's basically a series of temporal and spatial Fourier transforms, and you end up with the same figure that I showed you before. The best part of my work is that I don't have to deal with any of these complications, because this is the hard part that a lot of you already do. So I just take the end results and I try to do inversions out of it. All right, so one of the more fundamental concepts that one needs to really understand for understanding mode coupling is that whatever we see on the surface of the star or the sun is really an end result of how these modes, or whenever I say modes, think about these spherical harmonics, how they couple with each other, or how they start talking to each other. And whether or not a particular spherical harmonic talks to another depends on the perturbation that's present in, that's trying to couple these spherical harmonics. So just geometrically or intuitively, if you look at the very first panel, you see that it's the two modes are axisymmetric. And now if they are coupled by a perturbation which is constant, then you can just see that it's just going to be an even structure in latitude. And of course, the integral would be non-zero. In the second picture, the modes are the same, but the perturbation is just antisymmetric about the equator. As a result, the product would give you something which is antisymmetric about the equator. And now if you carry out an integral over the entire solid angle, of course, that's going to be an odd integral, and so it's going to give you 0. And in the final picture, it's a non-axisymmetric field. And if again, intuitively, if you take a product of these things, it's going to be non-axisymmetric in the azimuthal direction, meaning if you go along the equator, you're going to go as much in negative zones as much in the positives. And so it's going to integrate out to 0. And this is just an intuitive picture of how two modes are either coupled or not coupled in the presence of a perturbation. And you don't have to really go into the detail of the mathematics, but what this really is just selection rules. And they're enforced by these Wigner symbols, as we call it, or Clebsch-Gordan coefficients, if you're familiar with the quantum mechanical analog of this. And so if a mode is labeled by its angular degree L prime, another mode is L, and the perturbation has a structure which is S, then if these sum up to an even number, and if the sum of the azimuthal orders, which is like M prime, M, and T is 0, then it turns out that it will give you a non-zero value. So again, going back to the first case, it's really easy to see that that's true, because L prime is 4, L is 2, and S is 0. So they add up to give you something which is even. And of course, all of these are axisymmetric. as a result, m prime, m, and t, all of them are 0. So they sum up to 0. So it is not going to evaluate to 0. So it's a finite value. So whenever we write Wigner symbols, or whenever I show you these things, which is not going to be too much, this is what I mean by selection rules. And similarly, you can play around with these various combinations of L prime, L, and S, and see that all these selection rules are just summarized in this expression. So this is just to give you an intuitive idea of how the geometry of the perturbation is really important in terms of which two modes you're going to pick out in order to see the structure that's captured by them. So we could try to choose two modes which would constructively interfere with each other, depending on what perturbation we are trying to infer. For example, in rotation or in differential rotation, which is an odd even S structure in some convention and odd is in another, L and L prime have to be separated by an even number, and the ones which are separated by odd do not couple to each other. Again, differential rotation is not something that I'm going to talk about. So, but that's just a geometric analog. So coming to the part of what really sensitivity kernels are, it's just I felt it's more of a. I mean, it's very apt to give a coffee cup example in a COFFIES seminar, and so this is what. Yeah, so this is what sensitivity kernels would basically mean in terms of a coffee cup. So let's say you think about the coffee that you have, and you just put in some coffee, and that would be the background state of your system. And whenever you're trying to put a drop on the surface of the coffee, you can measure how the oscillations or the ripples are carried out across the surface. And from that, you can extract the eigenfunctions or the eigenstates, as well as the eigenfrequencies. And with the information of the eigenfrequencies and eigenfunctions of these oscillations on the surface of your coffee cup, you can understand what's happening or what's inside. So if there is, if it's just like, the background coffee, there is nothing fun going on. And whatever you expect theoretically is what you see from your observations. But now let's say you put a little bit of sugar in there, and that settles down and accumulates at a certain depth. And now if you put another drop of water or something on the surface, and you'll see ripples. And if you make observations of this, you'll see they're slightly different from what you would expect. And from these differences, which forms the data, which in this case is F, we can actually map back what the perturbation or sugar is in our case. If the kernel is a constant in depth, so it doesn't matter, what is the strength of your perturbation, it's going to have the same response everywhere. But usually that's not the case. And so what happens is very close to the surface, the kernels are very much stronger as compared to when you're looking deeper in the interior. And that's sort of, just nature's way of saying that, look, the farther you try to look in the interior, the harder it's going to get for you. And so any perturbation that is close to the surface, if it is of the similar strength or magnitude, will show up with a similar frequency perturbation in the data. So yeah, so this is a simple demonstration. But now, well, of course, the coffee cup in our case would be the sun. And any problem that I'm going to talk about from now on would be written in such a linear inverse problem form, where the observations are something like either frequency shifts, or it could be cross correlation of the mode amplitudes, and perturbations could be anything which is like rotation or magnetic fields or sound speed or density. For this particular talk, I'm going to illustrate how you do the same thing for magnetic fields or Lorentz stresses. And in the case of differential rotation, the panel on the left is the frequency shift. So the black line shows you what you would expect from the background state of the star. And the usual method to do this is to take a reference model, which is called the model S in many cases. And all the model is spherical symmetric and non-rotating, non-magnetic. And so it's a very simple, boring model. And if you calculate the eigenstates of the system, you'll see that they are degenerate in N and L, meaning that for the different azimuthal orders, they're all the same. So if I look at a particular NL combination, it all has the same frequency. So that's the flat black line. And in the presence of rotation, the eigenstates actually split up. It's mostly a straight line, but there is a slight curvature, which is where the differential rotation is actually, where the differential rotation actually shows up. But this has been possible, and this has possibly been one of the more exciting revelations from the helioseismology, where differential rotation has been so accurately imaged in the interior. But that was possible mostly because the form of the kernel was actually known for the rotation. But the closed form expression for the kernels of Lorentz stresses or magnetic fields haven't really been known until very recently. Or rather, people have been mostly trying to use very specific magnetic configurations, let's say toroidal or purely poloidal, at a certain depth in the star, and trying to do these forward problems to end up with, whether or not you can end up with observations which sort of closely match what you get from the simulations. But that's not really a formal inversion. And so unless we could go ahead and propose the closed form expressions of these kernels, formal inversions were not possible. A very brief mention of previous studies, as I already mentioned, actually carried out mostly focused on forward calculations of axisymmetric dipolar or toroidal fields. Zimbowski and Gude also did the same thing, but for near surface large scale toroidal fields. There are some other studies which focus on sunspot seismology, how the acoustic modes there's a reduction in observed power in the acoustic modes because of conversion into the magnetized waves near the sunspots or strongly magnetized regions. But again, none of these carry out a formal inversion. And the very first paper, in my knowledge, which does this correctly, and there's a lot of things under this envelope of correctly, is what we did in 2020, where we proposed these kernels, which were Hermitian and which treated the problem in the correct basis, as I'll show you later, for Lorentz stresses, which is the second rank BB tensor as a perturbation. And to go into it, a little bit of theoretical description in terms of what we actually did. So I guess equations of ideal image is something that all of you are familiar with, so I don't really have to explain that. And as I said, we always have this background model of the star, and in most cases, this background model is actually non-magnetic. And you can therefore linearize the background model because you already know that the observations are very close to what you expect, and therefore the tiny differences we can hope to be captured through linear theory, at least in the global scale. And yeah, so if you go ahead and linearize the ideal image equations, you would end up with a force operator or a magnetohydrodynamic operator, and that's just an eigenvalue problem thereafter. So what I write here in this cryptic integral form is just sort of the potential energy content in such a magnetized system. And of course, this is an exercise which I don't expect you to follow right away, but crucial part of what I'm trying to say here is that if you flip the modes, which is given by eta and xi, which are the modes that are getting coupled through a perturbation, which is through F operator, which contains the magnetic fields, then you would end up with something which is self-adjoint or Hermitian. And as a result, you have, I mean, that's what you would expect because, you don't have resistivity in your system, which would render otherwise. So the last slide, of course, which has all of these equations, is that what really does this potential energy encode? Because previous studies have mostly looked at acoustic perturbations, and there are these controversies of if you can accommodate all these mode conversions from acoustic to all these various kinds of magnetosonic fast and slow modes and all. So I just wanted to put here that you have the contributions from the shear Alban wave or the energy contained in the shear Alban wave or the compressional Alban wave in the operator, sound speed or the acoustic perturbations, as well as pressure driven and current driven modes. So we think we have a complete treatment here. And therefore, we can go ahead with this and formulate the kernels, which would have the accurate response that if there is magnetic field in your system, And if there are acoustic waves which come and strike a certain magnetized structure, we account for all these mode conversions that happen in between when we look at the frequency splittings. So I've been talking about the fact that we want to do magnetic inversions or magnetic field inversions, but magnetic field is not really the perturbation that we would be inverting for or imaging, because if you write out the Lorentz stress term, you have the curl of B cross B, and you see there are two B fields sitting in there, and since these are two B fields, we want to invert for B, so you have to naturally club them together. And therefore, you would end up with the second rank magnetic field tensor, which is the BB. Therefore, the inversion not only becomes B, which is the vector B, which is Bx, By, Bz, but actually you're going to invert for Bx squared, By squared, Bz squared, Bx, By, Bx, Bz, Bz, By, the six independent components of Lorentz stress. And after taking the force operator that I showed you in the previous slide, doing some crazy amount of tedious algebra, vector calculus, and generalized spherical harmonics, transforms, and all of that, you end up with this pretty horrendous looking beast in the orange highlighted area, and that's our Lorentz stress kernel. So I don't show all those steps, of course, but this was the most important bottom line of the paper. That's why I'm sort of trying to elaborate what all went into this. So the observations are the lambda k, k prime k, which you can think about in terms of either being frequency splittings or being cross correlation of mode amplitudes, as you may. The perturbation, which is the script H, which is color coded in red, is what we want to invert for. And yeah, as I already said, the kernels are in orange. And it's an integral linear inverse problem, as you see here. And there are well-known ways of solving this. So the next question is, okay, what did we do right? Or what do we think we did right when we formulated all these kernels as compared to previous studies? The first thing is, most of the studies, or I think all of them actually, considered a hydrostatic equilibrium. But the thing is, you need to consider a magnetostatic equilibrium if you want to correctly account for the zeroth order magnetic fields that you would be inverting for. So it's not only grad P equals rho G, but there's also a curl of B cross B, which comes from the J cross B term. And that is very, very essential in ensuring the Hermitian property of the operator. And all of this is found in the ideal MHD books such as Friedberg or Hoodblood and Poitz. And the second thing that we did right, we think, is to treat the problem in the correct basis. And this is something that I've mentioned before. So instead of using the spherical coordinates, which is radius or theta or phi, what we do is we carry out this transformation into what we call generalized basis, which is E plus, E minus, and E0. And the other important part is that you need to use the correct spherical harmonics. If we use scalar spherical harmonics, which is useful for scalar fields, or if we use vector spherical harmonics, which can be used to decompose vector fields such as velocity on the surface of a sphere, well, we end up with extremely unwieldy sort of identities which take us nowhere. But if you treat the problem in generalized spherical harmonics, you can leverage all the beautiful identities that come with it. And that's exactly what we did. And this has been routinely done in terrestrial seismology, where they have this fourth rank elasticity tensor. And therefore, of course, they would need a generalized spherical harmonic basis to carry out inversions of its components. And finally, once again, on the top right is the inverse problem. And now you see that there's a script B instead of the perturbation, instead of the kernel, and there's a H instead of magnetic fields. So the natural question is, how do you relate the H to the B? And all these expressions that we already have in the paper can take you from this cryptic looking H into things which are more familiar to the community, which is BR squared or B theta squared plus B phi squared and BR B theta and all these combinations. So we have stipulated all of these things in our study. And even though it looks a little intense in terms of the mathematics that's there in the paper, I think if somebody tries to go through it, it should be understandable. All right. And finally, these are what the sensitivity kernels look like. And I would like to draw your attention to a couple of properties, which is true for other sensitivity kernels as well. So if you look at the blue line over there, that corresponds to a mode which belongs to a higher angular degree, and that's very, very constrained or very, very shallow sensitive, meaning it's localized very close to the surface. But in the same picture, you don't see the green line, which is kernels corresponding to modes which are of a lower angular degree. And in the lower image or in the lower panel, you see that it's at a much lower depth. And there you cannot actually see the blue line at all. And you can only see some of the orange and some green line. So that just shows that modes which are of lower angular degree, which are these, in terms of ray theory, these modes which go through the interior of the star much more than the higher angular degree modes, which sort of bounce back from the near surface layers, are differentially sensitive to different parts of the star. And of course, if the signal to noise in the data was good enough, then one could use all these kernels to carry out inversions for different layers of the star by choosing the correct modes that you try to look at. We have a toy problem in our study where we try to build this image of the sun, where you have toroidal fields in the center, and there's poloidal fields near the surface, and there's a region where the toroidal fields mix and merge with the poloidal fields, which is the mixed layer. And so in the image on the left, you see that the green shaded area is the part where you have the toroidal field, and the red area is the transition zone or near the tapered line. And the blue shaded area near the surface is where the field becomes poloidal. And we assign numbers to this, which is sort of believed to be true. Of course, I'm not taking responsibilities of if this is exactly what's there in the sun, of course not. But if you believe that this is true, and if you set this up in the way we set it up, we can do the forward calculation, just like previous studies, using our kernels and see what sort of A coefficients we end up with. These A coefficients are nothing but a proxy for the frequency splittings that you would see. So I show here one of the models out of the 8 models that we have chosen. And the model M1 is supposed to be sun-like. And so for that, if we have used 2 modes, which is 2s10 and 5s110. And for this, you see for the mode which is 10 and has a lower angular degree, the A0 and A2 are, of certain values, fine. And 110, okay, it looks, there are a few numbers here. I'll show how these numbers compare to observationally what we have. But now if we look at a second model where you have the third layer, which is near the surface, to be multiplied by a factor of 10, which is why we call it high, which just means that you take that point on the surface and drag it up to make it 10 times stronger. You see that there's not much change in the A coefficients for the lower angular degree mode, but the ones with the higher angular degree shoot up 100 times. And this is simply because, as I said, the higher angular degrees are shallow sensitive. And so now if you're changing magnetic fields near the surface 10 times, and because the perturbations are BB instead of B, it becomes 100 times. And because the angular degree, if the angular degree is low, it's probing the internal layer much more than what it's probing near the surface. So even if you change a lot near the surface, whatever is happening inside, which is very strong magnetic fields, is sort of accumulating or flooding the signal. So changes near the surface don't really matter. There are other demonstrations that we have done where we have done the same thing for all these layers, and you see that depending on which mode you choose, you can see differences in the A coefficients. And this is exactly what I meant by probing different layers with different modes. And this is the final thing in terms of global coupling that I will be talking about. So what I show here are observational A coefficients, even A coefficients. It's important to know that these are even because the odd A coefficients are completely flooded by recordings which are just sensitive to rotation. So the even A coefficients are believed to contain information from structure, and this is at a solar minimum. And the orange line that passes right through it is just these A coefficients that are constructed by accounting for second order effects of rotation as well as mode coupling. All right, this is what it looks like in case of a solar minimum. But now if you go to solar maxima, you see that the orange line doesn't really start explaining the A coefficients, especially for the A2. And so there's a steady trend where it increases as a function of angular degree. And again, as I said before, the larger the L, the closer it comes to the surface in terms of sensitivity, which just means that what this is showing is all that the A coefficients encode are magnetic fields very close to the surface. And the higher you go, the more sensitive the kernels are. Therefore, the stronger the A coefficients become. We are currently in the process of trying out dynamo models through a forward problem, as well as trying to do the same thing in an inverse problem to see if we can explain this trend in A coefficients using our kernels. All right, so I have rushed through the global mode coupling, and now I think I have approximately 15 to 20 minutes for the local mode coupling, which is the more exciting part. Let's see how I do in this. All right, so if we try to go from global to the local, basically the change that we need to account for is the basis function. In global, it was these spherical harmonics, which are these ripples on the surface of a sphere. But now when you try to come to the local system, and if you zoom into that image, you would see that they are just plane waves propagating in this box. So that's just sort of going from the spherical harmonics to a plane wave exponential basis. And here on the left, I'm just giving a pictorial demonstration of a quiet sun, sort of a quiet sun patch. And these yellow grids are just trying to mark out different supergranules. And I'll be giving a demonstration of how inversions look like for supergranules at the end. But for now, you can just think about the fact that you take such a Doppler cube, and from the spectral and Fourier transforms, you would end up with these mode amplitudes, which is going to be phi as a function of frequency omega and spectral frequency or wave number k. And you take two of these, meaning you take two modes. And as we discussed before, you need to couple two modes to understand what sort of perturbations are captured by their interaction. And what you end up with are these things called B coefficients. I personally don't know why they're called B coefficients, but I guess it's just because there's already A coefficients that's taken up. And in simpler words, again, what these B coefficients capture are the cumulative effect of all internal perturbations that these two modes sort of feel when they start talking to each other. Now, if you can take these B coefficients, which are in K and K prime, K being one of the modes and K prime being the other mode, and since K and K prime are just wave numbers, you can do a 2D Fourier transform back, or inverse Fourier transform back into the spatial basis, and this is how it will look like. I just put this image because it's easier to think about how something looks like in the physical space. So now if we have a sunspot, or anything for that matter, you can decompose that in at least the surface feature in the plane wave basis. But then, as I'll show in a few slides, this is extremely suboptimal, and we can do better, basically. Yes, and this is sort of to drive home the fact that when you have a sunspot, it's circular in structure, and now if you have to resolve that in plane waves, the traditional approach, then you would need many plane waves to do that. And so the first equation here is just what we had from the global mode coupling treatment, where you have an observation, you have kernels, and then the perturbation. The exact same thing happens for the local mode coupling. Well, of course, the calculations are all in the basis of plane waves, but the overall form is the same, where you have the observations, which is these lambda terms, k prime, and there are kernels which are sensitive to which modes you're looking at, of course, which is k and k prime. And an important thing to note here is that the perturbation, which is script h, has this subscript q. And now we already talked about selection rules in global case, and we saw that these two modes are coupled by the perturbation, and the same thing happens for the local coupling, where you have these two exponentials and they're coupled by the exponential or the plane wave, which contains the wave number information for the perturbation that we're trying to look for. And of course, this integral evaluates to a delta function, and that gives you a selection rule which says that if you're trying to understand or invert for features which has a wave number q, then you can only stick to a specific set of combinations of modes which have wave numbers k and k prime. Although we will be observing a host of k and k prime combinations, we'll only have to restrict ourselves to a subset of that when we are trying to invert for a structure which has its wave number as q. So to just make it easier to understand whatever I said, if you have a hypothetical perturbation in the form of this left image, which is something that I obtained from JSOC, that's just the BR squared component of a sunspot. But that's not important what exactly the perturbation is. But if you take that and if you carry out its Fourier transform in space, this is the picture that you get. Now, let's say we're interested in the Q that is given by the grid, which is in the white square. So that's Q1. So that is the very first inverse problem that you have. And so you can only choose the K primes and Ks from data that has that selection rule playing out. But now if you try to choose a separate Q2, then you have another set of K prime K. Similarly, you can do this for all the wave numbers that you're interested in, and ultimately combine all of them to get back the inverted structure. But then this just means that the whole problem becomes this huge slew of separate independent inverse problems, and each of these inverse problems are constrained by at least n times less number of data than that's available to you. So that also means that for the people who actually do inversions, you have to sit down and monitor each L curve separately, which controls the signal to noise in the system. And that's extremely unwieldy and inefficient. So what is the point here? The point is that this is very similar to the classic example of when you have an elephant, and if you ask blind people to try to feel the elephant in different parts and say what that actually is, none of them will be able to say that's an elephant. Some people would think it's a snake, some would think it's a rope, and so on and so forth. And we are literally blind in terms of people who are doing helioseismology because we don't know what we are trying to, what it looks like. But so if we can maximize the observables, then we can infer our understanding or infer the structure to a much better signal to noise in terms of how well you can model the system. So what if instead of the first equation, our equation, the equation for the inverse problem looks like the second one, where P are the perturbations that are unknown. And the important point to note here is that it does not contain a wave number label, which means that each perturbation is actually constrained by all the KK primes that you have. And this can only be done if we choose a basis which is, which is inspired from the actual structure that we think exists there. And the way to do that would be to just look at the surface and understand and sort of, define a contour. In case of a sunspot, that would be a circular contour. So what if, let's say, for an axisymmetric perturbation or sunspot, we had a basis function that looks like this, or something that looked like that, or that, or that. These are all nice axisymmetric perturbations. And what these are these things called numerically evaluated Slipian functions. And if you look closely, you would see that the very first image on the top left is very much confined within the black dashed circle. And as you go down, you see that there's like leakage happening outside. And this is where Slipian functions are nice, because you would only want to use the number of Slipian functions that are optimally confined within the area of interest. And that forms a complete basis for the perturbations that you are trying to resolve. So in this case, you see there's a factor called lambda, which is 1 here, which just means the power of the Slipian function in the entire R2 space divided by, the power inside the black dashed line divided by the power in the entire R2 space. In this case, it's just unity because there is nothing outside the black dashed line. But now as we go towards higher and higher lambdas, higher and higher labels in lambda, we see that it starts emanating outside, which just means that we would have to stop at a point where it's like optimally confined. And there's something called the Shannon number. These are the details, but it's possible to choose arbitrary basis functions for perturbations that you're trying to invert for. As a very simple example, we have this axisymmetric perturbation. And there you see there's like ringing outside that black dashed area. What this actually is an average supergranule. But on the image on the left is what you observe, and the image on the right is what you reconstruct if you use the Slipian functions that I showed. And there are only 3 peaks in, as you see in the coefficient plot, which are the 3 different axisymmetric fields or the axisymmetric basis functions that actually capture the structure in this case, instead of a few thousand perhaps if you use plane waves. And this is a demonstration for the sunspot. Again, I qualify my statement when I say that you can invert for sunspots using this method. I don't think you can. But this is just a demonstration that you can take a generic perturbation and you can use this method. So on the left panel is an HMI observation for the 6 Lorentz stress components. The central panel is what you have from the reconstruction. They're pretty close. And the panel on the right is the difference between these structures. And as I already showed in the very first slide, you can basically go crazy with these basis functions. You can choose whatever domain in the physical space and in spectral space. And here I show a cat and a duck. And this is the same thing, but for an emerging active region. This was used in Birch et al. 2019. The figure on the very left. The figure in the middle is what we get when we use the special basis functions using the Slipian functions, and the figure on the right is just the difference between them. So this just shows that when you're trying to carry out these inversions, you're only focusing on what you're interested in and not the noise outside. And finally, I'll show you some of the demonstrations after all the difficult, bad-looking equations that I've already shown you. So the first example is for an emerging active region, and these are very recent results, and this is under preparation. So the picture on the very left is what you get for an inversion when you carry out when you take an emerging active region and you sort of use the B coefficients from that and you try to invert for the flows. The picture in the center is what you get from let's say a poorly put together averaging kernel. So the point over here is that for all the 3. And you see that the overall features are very similar. So for the Slipian basis, which is on the extreme right, you see there's like a central blue patch, and there are 3 or 4 red patches. And these patterns are consistent across all of these 3, meaning the plane wave basis and the Slipian basis have similar performance at the surface. But then that's not the end. What we want to do is we want to invert for as a function of depth. And for the plane wave basis, when you have many separate independent problems and different L curves, you end up with poorly constrained inversions. And that shows up in this insane amount of rippling as a function of depth. But for the Slipians, you see it's very nice and smooth. And we get a very nice L curve, and it's one single problem. And you use all the data that you have at your disposal. And there is no bad oscillations. And so I think this is incredible. I mean, I'm personally extremely excited about what we had got. And this was as recent as, I think, last week. So yeah, emerging active regions, we are getting promising results using the Slipian basis instead of the plane wave basis. And this is just how the same thing looks in depth. It's just one of the cool animations. That's possibly the coolest animation that I have in my slides. So as you go deeper and deeper, you see that because of the incompressibility condition being imposed, the inflow regions slowly change into outflows. And the red contour is the hand-drawn Slipian contour that we use for this study. But then I told you this is an emerging active region. So the picture over here on the left is what you have 30 hours before emergence. And the picture on the right is what you have 13 hours before emergence. And yeah, it's an emerging active region, so you should expect to see things emerge. And this is insane in terms of what we were getting before and what we get after using Slipians. And finally, I'll take 2 more minutes. This is what you have for inversions that we are doing currently for average supergranules. Wait. 1 sec. Do you see my animation? Yeah. So you identify the center of the supergranules and then you start averaging them. And at some point, you see that there's a constructive interference happening at the center, and everywhere outside, it's just basically noise. And what we end up with is a coherent summation of all the supergranules and B coefficients for an averaged supergranule. And so if you zoom in, that's what it looks like. And finally, when you carry out the inversion, this is what we have. There is not too much to say other than what you already see. There's like inflows at the edges, and then there's like outflows from the center, and there's this nice spirals, and the length of the arrows shows the velocity. And you see that there's like smaller arrows at the bottom because the density is higher, therefore divergence rho v has to be conserved, and so velocity reduces. And finally, this is the acknowledgement slide. I have, of course, not done all of this alone. There have been people who have helped me a lot. And this work of the Cartesian mode coupling was supported by the Elizabeth H. and F. Dahlen Award over the summer. And I would leave you with a slide which contains what I have shown you, which is the first panel, and also what I have not shown you, which is things which we have done with flows. So if you're interested, please ask me about this. So very briefly, on the very left at the bottom is we have tried to carry out rotational splitting inversions using, when we fit for the mode amplitudes using a Bayesian inference. And in the center is a more recent study where we try to ask the question, is coupling important in the near surface layer of the sun when we are trying to invert for differential rotation? The answer in one line is no. It's very tiny. It's 500 times lower, but it is what it is. And on the very right is something that I already showed you, which is there a possibility of doing global magnetic field inversions using the kernels that we have, given the fact that the A2 coefficients actually have a significant departure during solar maxima from what you expect in terms of just second order couplings, second order effects of rotation and mode coupling. So yeah, that's my time. Thank you. I would take any questions if there are any.
Yeah, thank you very much, Srijan. Very interesting talk. And yeah, if we have any questions, please go ahead and talk away.
I think the first question in the chat was from Shay.
Yeah, just so some of the work that I've done in the past is looking at the assumption of symmetry in helioseismology or at least in local helioseismology, and whether that's a reasonable assumption to make. It kind of seems like the regions that you're looking at are oddly shaped, but the assumptions that are going into your inversions is that everything is symmetric. Is that gonna kind of mess up some of the inversions that you're doing?
Sorry, what do you mean by that we use like there's inversions? There's symmetry in our inversions.
So you're talking about like being able to model a sunspot in terms of its its symmetry, but that's not necessarily something that's like.
Oh no, yeah. Right, like, I mean, the sunspot was just a very trivial example because most of the time, it looks more symmetric than an active region. So I just chose a circular looking slip-in function, but you could just, take a pencil and draw literally the exact contour of a sunspot, which is not symmetric, and use that as a highly asymmetric slip-in basis to do the same problem. Just like, for example, here. Like this is for active regions, emerging active regions, but this is absolutely not symmetric. So you could do the same thing for sunspots as well. We just chose it to be a circle because it looks circular, but we could have chosen to be anything else. For, I think you're talking about this, right?
Yeah, that was what sparked my question.
Right. No, you could like, if you see the two lobes, there are two lobes in by squared. You could just pick out one of the lobes and literally draw a contour around it and make it as complicated as you want. And you would get similar basis functions for those. And you could just carry out an inversion just on that. If that makes sense physically, of course, but yeah. But there is no intrinsic assumption of symmetry.
Okay, I think a similar question was asked by John. So, John, if you want to ask a question.
If I may, yeah. So I think you've cleared it up quite well. So the Slipian functions that you use, basically you draw the contour and then you create your basis functions out of that. And I think that does have quite a lot of applicability in the sense that, as long as you have a good enough image of the active region on the surface, you could draw your own contour. I guess my question is how much does that influence the information that you get from the subsurface structure?
Yeah,
because that does kind of assume that the structure that you see on the surface is also carrying through all the way down.
Exactly. Yeah, exactly. So this is something that I had been also thinking initially when I came up with this. And the answer is, this is one of those trial and error methods. So what I would personally do if you ask me to do the inversion right now is I would define the minimal contour, like most tightly constrained contour, do an inversion, see what we get. Expand the contour slightly more, do an inversion, see what we get. I would expect if we are at the point where we are choosing the contour to be large enough, which captures all the physics that's going on in the subsurface, you would start getting inversions which would have broadly consistent features.
I have two follow-up questions to that, and I promise I won't take any more time. The first question is, could you possibly have kind of like a depth-dependent basis function? So choose different shapes with depth. And then I guess the second question is, how long do these inversions take for you to run?
Oh, the first question is a little more involved mathematically. So in the case where you have different Slipian functions as a function of depth, then I guess, I think I had thought about this at some point. There was one subtle point which I don't recall right now, but the broad answer is that there was some problem with that. I'll get back to you once I recall what the point was. It's a little involved because there are some identities that's at play here. About the second question, these inversions do not take long at all. Apart from, there's only one issue with these inversions, which is, when you look at the kernel expressions that I showed you here, you see that kernel is k prime, which means it contains all the modes, first of all the combinations of modes. There's a j index, which is radius, and there's an alpha index, which is the number of Slipian functions that you use to discretize your horizontal. It's a ginormous kernel. And so you would either have to, when you are doing linear inversions, there are these k transpose k operations that you have to do, and then you have to take the inverse of that. So when you carry out the k transpose k, you would have to either do that in a system which has a large enough RAM to directly carry out the matrix contractions, or you would have to do it one row and one column at a time. So that is the bottleneck. But in terms of just carrying out the inversion, it doesn't take any time.
Got it. Thank you very much. Very interesting work.
Thank you so much. But I'll get back to you on the first question. Yeah.
Okay, next question I think is by Georges. Georges, if you want to ask. If not, I can just read it out. So he asked, how deep in the interior can this method detect emerging active regions? And also, how many cases have you explored?
Well, how deep? So I guess that question has two layers. One is, are you asking theoretically how deep can we go? That relates to how far the sensitivity of the kernels exist. And the other is what sort of noise we have. What we're doing here is like an averaged, like we average the emerging active regions over certain windows of time. Exactly the same thing that has been done in Birch et al. Before as well. And so we see from that that we think reliable inversions. By reliable I mean the point in depth up to which it's not dominated by regularization but dominated by data is, as you see in the image, is approximately 3 megameters. But that has two competing things playing in. One is the sensitivity of the kernel itself, and the other is the signal to noise in the data. For emerging active region, signal to noise is absolutely horrendous. And we could only get this because we are better parameterizing our model parameters itself. But if you ask me the question about how far the kernels go, I would say just from all the kernels that I have looked at, reliably, I would say 10 megameters.
And I guess, yeah.
Irina had her hand up, and then Nick.
Right.
Yeah, thank you. I have several questions. Probably some of them I will keep after Nick. So first, I don't know, it is question or comment. What I noticed for your second part, you even didn't mention any kind of testing with models. So it make me concerned how reliable this technique is.
Sorry, can you repeat the first part of your question again?
Have you even tested your approach with models, with numerical models?
Okay, so you're asking synthetic inversions? When you say numerical models?
I mean to test your technique presented in second part of your presentation, you have to use models first to make sure what you're actually measuring, what you're expecting to measure. Have you tested?
I'm not exactly sure what you mean by models, but we are just using, model S as the background model, which was proposed by Birch et al. 2002, and that has been used by all of local helioseismology. And the second thing is we did do synthetic inversions, and yeah, those were fine.
So just follow up comment, in very beginning of your talk, you really criticized model S. So and because it didn't include many effects, so according to your logic, you don't have to use it. It just commented.
No, that I didn't criticize. That's amazing, because if it had accounted for everything, then I would be doing my thesis in something else right now. But no, it's close enough. It's close enough, but it still doesn't capture everything. Yeah. So it's a good starting point.
Yeah, but when you discuss in beginning of your talk about global inversions,
yeah,
you decided don't use for some reason model S, if I understood correctly.
No, we do.
Instead,
we do.
Okay.
We do use model S. All the kernels. Yeah.
Okay. Yeah, it's good. But you use radial profiles of magnetic fields. And my question is how you obtain such profiles. For me, it looks like, I don't know, what is physics you have in mind when you draw these profiles for magnetic field? So
it was a toy problem, as I said, and it was just inspired by, the fact that the sun has a sort of, if you think about it in a washed out fashion, a dipolar structure in the solar minimum. And we were thinking about the solar minimum at that point. But like the simplest case is it's a dipole with a few Gauss at the surface, 10 power 5 approximately at the tachocline, 10 power 7. I had to find very hard. I had to search very hard to find is there any paper which says what is the core magnetic field? And like, I think it's like 10 power 7, 10 power 6 Gauss. And so I just assume it's toroidal right from the center to the tachocline. And then it sort of has a mixed nature where it's toroidal and poloidal, and then it merges to just become dipolar outside. There is no physical, there is no directly inverted reason for this. Like, I don't do inversions. I just cook up something to see what sort of numbers I get. And the numbers that I get are very similar to what you observe. So that's encouraging. Yeah, so that's just a toy problem. It's more relevant for astroseismology. Some of the cases I didn't show here, where the core magnetic fields are actually felt and sensed by the G modes. And I didn't show this because it's mostly a solar-based talk here. But yeah, so to answer your question, I just make that up from whatever known literature is there, some numbers here and there, and sort of the expected 0th order magnetic field profile of the sun. Very, very simple. There's nothing complicated there. That's all.
Thank you.
Thank you.
All right.
Hey, thanks for an interesting talk. A few questions. First of all, as a mathematician, I didn't get what your definition of Slepian functions actually is. I mean, normally these functions are solutions of a Laplace's equation or a Sturm-Liouville problem on some sort of geometry. Are they the same thing in this case? Is it just?
It's exactly that. Yeah. So if you define the okay, let me try to go there. Yeah. So there's this factor lambda, which just defines the localization of the Slepian functions within a certain domain, which is given by script R. Now, if you try to maximize that expression, you would end up with the integral Fredholm equation. And what happens is that integral commutes with a separate differential equation whose solutions are well known. And so you can then solve that differential equation as a tridiagonal system numerically to end up with all these eigenfunctions. Yes. So ultimately,
so they're still sort of linear eigenfunctions, but on a very weird domain. That's the deal.
Exactly.
Not
A weird domain both in space and in spectra. You need to specify these two things.
Okay, cool. Thanks. My other question was, given an observation, a perturbation observation, you've now shown that using this methodology, you can invert it and sort of get some sort of idea of what magnetic field may cause that perturbation. But is it unique? Can you separate that from that perturbation being caused by other effects?
Yes, this is a very good question, actually. I didn't put, okay, I don't think I should even search for it, but I don't think I have it. Let me see my supplementary slides. No, I don't have it. But anyway, so the answer is yes. So there is a competing effect between the magnet. Sorry, I'm not sharing my screen, I guess. So there's a competing effect between sound speed perturbations and the horizontal magnetic pressure, which is bx squared plus by squared, has a kernel which has a similar form or the same form off by a factor as the sound speed, meaning that when you try to do an inversion, it is not just bx squared plus by squared or just sound speed that you'd be inverting. Right. You would be inverting for a combined quantity. And now how you would disentangle this would be yet possibly another inverse problem, given some other observations or physics that you know from the system.
Okay, that's very interesting to know. Thanks very much.
Thank you.
Okay, let's do one last question from Georgios.
Yeah,
Georgios asks, would this method of detecting subphotospheric structures work when an emerging flux tube emerges right next to a pre-existing active region?
Right. So I would start off by saying that as soon as you start having very strongly magnetized structure near the surface, for example, sunspots or flux tubes from active regions, what happens is we have made the assumption that this problem is nicely linearizable. But then this magnetic field, as you know, in a sunspot, pushes out all this material from there and causes the Wilson depression. As soon as you start having the Wilson depression, that goes into the nonlinear regime. So you cannot capture your perturbations through linear perturbation theory. And so at that point, you would start using a full simulation as a forward problem when you try to do this inversion. So I don't think this particular methodology can be applied directly when you're trying to invert for sunspots or very strong magnetic fields. But you can carry forward the perturbations, the basis functions to, parameterize your basis functions when you do the simulation-based inversions as well. So, so answer is yes and no, but in two different senses.
All right. Yeah, I think we're a bit over time, so let's thank Srijan again for this very interesting presentation.
Thanks, Srijan. That was a really
So-
nice talk.
Yeah,
Thanks so much.
Great.
I hope everyone enjoyed. I think I rushed a bit, but I was too excited to show everything that I have, because like this is the first time I'm showing it to a helioseismic group who are doing exactly things that I love. And so, yeah, I hope all of you enjoyed it. If you have any questions about anything, please let me know. There was one question that I have myself thought about, somebody asked me and I forgot about the answer. I will get back to you once I recall what the exact mathematical reason is, but yeah, thank you so much for the opportunity. I hope to see you all sometime in some conference or something.
All right. Yeah, thank you, Srijan.
Thanks, Srijan.
And,
Thanks so much.
Thanks, and good luck with your defense.
Thank you.
yeah, that's right. Good luck. All right, then, yeah, have a good day, everyone. See you soon.